Before we dive into the deep mathematical representation of the system, let's just simply try to control the system with the PID controller. The PID controller is one most popular controller in the industry. To implement it, you may not need serious mathematical modeling. So let's just try to implement various PID controllers with the simulation. I believe this actual experience of the PID controller will give you a solid ground to further discuss abstract math and so on. So if you're ready, let's get started. Now we are going to talk about the PID controller. However, even before that, please allow me to briefly go over a few jargons that I will be mentioning. From the previous video, we saw that the mass spring damper system oscillates while its magnitude is decaying. And we call that as exponential decaying with oscillation. To describe such behavior in math, people use the exponential function with a negative real number and an imaginary number. Or, together as a complex number is its exponential part of the exponential function. We'll discuss why the imaginary number represents an oscillation later. Anyway, some systems come without oscillation but only decays. And it looks like this graph. A simple exponential function with a negative real number. And we just call it an exponential decay. We saw that our spring mass damper system was stable by default. All our previous system output was exponentially decaying with oscillation. However, for some unstable system by default, the output will be exponentially grow, or casually people call it the system response blows up. Likewise, the system response can exponentially grow with oscillation. Again, there is an imaginary number with a positive real number. To wrap up, the terms like exponential decay and growth with and without the oscillation is the jargons I will be mentioning, and I'd expect you to be able to recall these graphs. And we'll discuss the detailed mathematical representation in Chapter 3. One last thing I wish to talk about before going over the PID controller is the block diagram. Here's a simple flowchart of our simulation environment. On the left-hand side, I copied the code of our update control output function. As I mentioned previously, the return value of this function is the input of the car's acceleration. Then the game engine will calculate the physics and update the car's velocity and the position accordingly. The newly updated position and the velocity will come back and invoke the function again. And then the function will calculate what would be the proper acceleration of the car at this very moment to reach a certain position. And this loop will go on until it reaches to the target position. If I draw the flowchart formally in a more engineering sense, it would look like this, and people call it a block diagram. On the left, in the blue letters, I stated the reference signal, desired signal, set point, or set point signal. This is just a value. If you remember from the previous video, I called the graphs as signals. But we know that the graphs were made of the data, which is a set of numbers like position, velocity, and acceleration. So when I say signal, it's just a set of values or a value itself. For instance, the set point can be the value for our targeted position and velocity. Simply, the error is the difference between the target or desired value and the current value. For example, if our target position is 5 meters, and the current position of the car is 1 meter, then the error is simply 4. Then, based on this current error at this very iteration, the controller will calculate a proper input for the system, and the system will respond to it. Next, the observer or sensor will measure the state of the system like position and velocity. And at the next iteration, we'll calculate the error again because the current value has been changed due to the previous output. Hopefully, if we design the controller properly, at this time, we'll have less error. And the loop will go on until the error gets to 0 or a certain level of error that the engineer can accept. For the PID controller, the high-level idea is the same. So let's now see how the PID controller can be implemented.